Hi everyone, it's a pleasure to be joined by you here today. And in this presentation, I'll be highlighting the key contributions of our paper titled RCM Constrained Manipulated Trajectory Tracking Using Differential Kinematics Control. My name is Omar Rayyan and I'm an undergrad at NYU-AD. Now this paper has been a collaborative effort between myself as well as Sir Vinicius, Nicholas and Professor Anthony Zas as part of the Center of AI and Robotics at NYU-AD. So what is minimally invasive surgery? As most of you probably know, MIS are types of surgeries that are performed through small incisions. Now that is done for several reasons, mainly being to prevent or to reduce the recovery time of patients after the surgery. So the main distinguishing point of MIS compared to other surgical techniques is that all of the tools as well as the instruments that are to be used in the surgery have to pass through that insertion point continuously during the surgery. Now, robot-assisted MIS can be thought of as an evolution to MIS, in which it utilizes surgical systems to improve and enhance the accuracy of such movements of instruments and tools within the human body during surgeries. And within the field of robot-assisted MIS, this constraint that arises from the insertion point is referred to as the remote center of motion constraint, or RCM. And the images that you see here on the right of the screen is for the Da Vinci surgical system, which is one of the most prominent surgical systems that are used nowadays in hospitals around the world. So such systems such as the Da Vinci, they adhere to the RCM point constraint by having a mechanical structure of a manipulator that is automatically, or let's say passively, adhering to the RCM constraint, such as the video that you see here, in which this is a dual parallelogram design. And the way it works is that regardless of the movements that are done to the joints, it is structured in such a way such that the tool is always going to go through the RCM point at all times. Now, an obvious drawback of having or requiring a specialized manipulator to carry out a task is that the RCM point or the insertion point is going to be a property or a function of the mechanical structure or the mechanical design, resulting in a reduced adaptability and a reduced flexibility to the surgeon during surgeries in picking this initial insertion point. Now, our objective and our goal in this paper is to create a framework of actively controlling a manipulator while adhering to the RCM constraint. But this is to be done algorithmically rather than mechanically, meaning we no longer require a specialized manipulator and we have more freedom in picking the RCM point since it's no longer a function or a property of the manipulator itself. And this overall would result in an improved flexibility and adaptability of the manipulator that we have in adapting to different insertion points in different surgeries. So to create this framework that I just mentioned, the first step would be to formulate the tasks that we have. The first being the RCM constraint task, where we're always trying to pass through that RCM point regardless of our position in the patient's body. And the second being the tooltip tracking constraint, where we're always trying to follow the desired trajectory of the tooltip position. So if the dotted semicircle here is the patient body, then we can define this point as being PF, or the RCM point, and this point as being PT, or the position of the tooltip. We can then attach a frame at the end of the tool and define lambda as being the length of the tool that is currently inserted within the patient body. And notice here all of these variables are functions of the joint position Q, except PF, as it is always constant, since the RCM is constant within our task. So as we just mentioned, we define this point as being PT, the tooltip position, and this point as being PF, the RCM position. Then if we subtracted these two vectors from one another, PT minus PF, then that gives us the vector that is from PF towards PT, which is also equivalent to the Z component of lambda. Now, the issue with this formulation is that we don't really care what lambda is as long as lambda is positive, because as long as lambda is positive, that means the tooltip is inserted within the patient body. So in order to get rid of the lambda component, we can pre-multiply this whole formulation with the transpose of x of t. And as you can see here, on the left side of the equation, we get x transpose the transpose of x of t, but on the right side of the equation we're going to end up with 0, and that is because x of t is orthogonal to z of t, therefore their product is 0. Now doing the exact same thing but with y, we're going to get a second equation with the exact same thing but with y instead of x, since y of t is also orthogonal to z of t. So now that we have formulated two equations for the RCM constraint, we can go ahead and write the task function for the RCM constraint as well as the tooltip. Beginning with the RCM constraint, it is simply those two equations that we have just derived. And as for the tooltip tracking task function, it is simply the position of the tooltip at any point of time subtracted from the desired position of the tooltip at that same time. And now that we have the task functions that we need, we therefore want to have these task functions converge to 0 exponentially. And to do so, we can implement the controller as being the rate at which the task functions are changing as being equivalent to minus ki multiplied by that task function, where ki signifies the gain at which the task functions are converging to 0 exponentially. And in order to do so, we need to first find the rate at which the task functions are changing. Beginning with the RCM task function, we can start off by defining the Jacobian of the task function for the RCM constraint as being the partial derivative of the task function in respect to the joint positions q. And once we have that Jacobian, we can then multiply it by the joint velocities, and using the chain rule, we can see that that will be equivalent to the rate at which the task function is changing with time. Now, as for the tooltip tracking task function, we can see that the rate at which that changed with time can be found out by simply taking the derivative of both sides of the equation in respect to time. And we're going to end up having that the rate of change of that tooltip tracking task function is equivalent to the velocity component of the Jacobian multiplied by the joint velocities of the manipulator. So now that we have computed the rate at which both task functions changes, we can go ahead and write down the convergence functions for both constraints. And we can see here that we're going to end up having 3 equations for the tooltip tracking constraint and 2 equations for the RCM constraint, resulting in a total of 5 equations. And when we compare that to the ICAR'23, which have 7 joints, and it is the manipulator that we ended up implementing our controller at, we can see that we're going to end up having 2 extra degrees of freedom, meaning we're going to end up having an infinite number of solutions. So to solve for that, we ended up implementing our controller as a quadratic program, where the higher priority was set for the tooltip constraint, in which, while it's adhering to that constraint, it is also trying to minimize the RCM error. And note here that we have added a regularization term in which it is used to maintain a lower velocity, and it is also used to ensure that there is a unique solution to our problem. And note here that since our quadratic program doesn't have any inequality constraint, we can write it down as a system of equations that can be solved analytically, where gamma in this case is the Lagrange multiplier. So one more thing that we have analyzed in this paper is how much of an effect does the insertion ratio of the tool has on the RCM constraint error. And we have came to the conclusion that if we take the ratio of the length of the tool that is outside the patient's body to that is inside the patient's body, then that is proportional to how much of a small change is required by the end effector of the manipulator to cause a small change in the tooltip of the tool. And let's take an example. So if we wanted to move the tooltip at a rate of 1 centimeters per second, then if we had an insertion ratio of 5, then that means we'd have to move the end effector at a rate of 5 centimeters per second. Meanwhile, if we had an insertion ratio of 1, meaning that the length of the tool that is inside the patient's body is equivalent to that is outside the patient's body, then that means we'd only have to move the end effector at a rate of around 1 centimeters per second. And it's quite obvious that if we had to move the end effector less, then the RCM constraint is more likely going to be lower than it is if we ended up moving it more. So as you can see here, this is a labeled image of our experimental setup. This is the ICAR'23 R820, which has 7 joints. And as you can see, on its end effector, we've attached a tool and down below it you can see the Aurora tracking device. Now we use two main methods in order to measure the accuracy of our adherence to the RCM constraint. The first method is an internal calculation method in which we are using the formulation of our forward kinematics to measure the deviation from the RCM point, and the second being an external way of measuring this accuracy, which is using the Aurora tracking device. So at the tooltip we've attached an electromagnetic emitter, and the Aurora tracking device works by positioning and finding the exact position of that tooltip in real time. Therefore, we were able to verify our results using two methods. Here's a sped up version of our experiment using an insertion ratio of 3. As you can see here on the graph on the top left part of the screen, we are measuring the accuracy using, as I mentioned previously, using both the Aurora as well as the forward kinematics evaluation. And it is important to mention here that the manipulator that we're using didn't have a controller for us to control the joint velocities, so we ended up having to numerically integrate the joint velocities that we got and send the joint positions to the KUKA IWA 14. So as you can see here, for the tooltip tracking error, we got an average error of 0.78 millimeters when measured using the forward kinematic formulation, and 1.1 millimeter when measured using an external electromagnetic tracking system. Now, as for the RCM error, we measured it using two different initial insertion ratios to prove the points that we raised when we were analyzing the effect of the insertion ratio on the RCM error. So when we had an insertion ratio of 1, we got an average error of 0.4 millimeters, and when we changed the insertion ratio to be 3, we got an error of 1.5 millimeters, which is expected given the analysis that we've done in the previous slides. And that's it. Thanks for listening.